Alright class, we're going to go ahead and do the last problem of this problem set. And the problem is asking us, the tides are created by gravitational attraction of the sun and moon on Earth. Calculate the net force pulling on Earth during a new moon, a full moon, and a first quarter moon. So this is the force of gravitational attraction, and it's going to be pretty easy. The setup for these problems is the same just about as the last ones that we have been doing, except a little bit of a twist, a little bit of an extension. So it gives us, here's the sun, and let's go ahead and draw a picture of the sun. Let's see, sun, happy sun, it's beautiful sun. And it's saying that the moon is over here, and the Earth is over here. Here's the Earth, here's the moon at three various points, yada yada yada. And we need to calculate the force, the net force of attraction. So we're looking for net force of gravity, let's say F net. That's going to equal G, mass 1, mass 2, distance squared, just as we have been doing. Except, if we're talking about the waves on Earth, the tides, the moon, its gravity, when it's here, is going to be helping the sun's gravity. And in problem A, it's saying, go ahead and the new moon, this is the new moon. So F net, because here is the tide and here is the moon, both the sun is pulling on the water here from Earth's oceans in the same exact direction as the new moon is. So the gravitational pull of the moon and the sun on Earth's oceans is going to be additive. So we're going to say F net is equal to F moon Earth plus F sun Earth. So to solve the problem, we're going to need to go ahead and do some calculating. We're going to need, let's go ahead and do F sun first. F sun Earth. That's going to be equal to G, which is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. And that's going to be multiplied by the mass. Go ahead and pick one of them first, say the mass of the sun, which the problem gives us the mass of the sun at 1.99 times 10 to the 30 kilograms. And the mass of Earth in the problem is 5.98 times 10 to the 24 kilograms. All divided by the distance between them, between the Earth and the sun, is 1.5 times 10 to the 11th meters, and we're going to square that. When you plug that in your calculator, you're going to get 6.67 shift 10 to the negative 11 times 1.99 shift 10 to the 30th, 5.98 shift 10 to the 24th, divided by 1.5 shift 10 to the 11th squared. That's giving me 3.528 times 10 to the 22nd Meter squared cancels meter squared. This is force, so newtons. Kilogram squared cancels kilogram squared. Meter squared cancels meter squared. Only things left, newtons. Newtons is my units for that. So the force of the sun to Earth is 3.528 times 10 to the 22nd newtons. All right, now we got to calculate the force of the moon on Earth. So in all cases, the force of the moon on Earth is going to be the same because that distance is never changing. So we're going to go ahead and use the same equation, g times the mass of the moon. So I'll go ahead and rewrite it. G times the mass of the moon times the mass of Earth. And that's going to be over the distance squared, which, plugging this into our calculator, I can write it out for you. 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. And again, times the mass of Earth,